Welcome back.
While our push button works, hardware buttons have a physical floor called bouncing. When you press them, the metal contacts bounce rapidly, causing the Arduino to see multiple presses in many milliseconds. Today, we will fix this by implementing a debounce mechanism directly inside our class. In the header file, we add 4 new private members. About the delay, this is the debounce time. The purpose is that when you press a mechanical button, the internal metal contacts don't close perfectly. They bounce or vibrate, creating a rapid sequence of high-low signals for many milliseconds. About the state, this stores the last stable logic state of the button. Purpose: it serves as a reference to compare against the instantaneous value from digital read. If the current reading differs from state, it means a potential change has occurred. Next is ignore until. This is the LARCAP timestamp. Purpose: it records the exact point in time when the program is allowed to start caring about button state changes again. Finally, underscore has changed. This is a status flag. Purpose: it marks that the button state has just flipped from high to low or vice versa. And in this class we have a new method called hasChanged. In the constructor, we initialize these values. Delay equals 100, means sets the default debounce delay interval. A value of 100 milliseconds is quite conservative and very safe to stabilize our signal. State equals blah blah. This line is crucial for defining the idle state rest state of the button. If using input pull-up, the microcontroller uses an internal pull-up resistor, so the pin sits at high when the button is not pressed. If using input typically with an external pull-down, the pin sits at low when at rest. Ignore until equals 0 initializes the LARCAP timestamp to 0. This ensures that as soon as the program starts running, the button is ready to be read immediately without waiting for any pre-existing delay periods. Underscore has changed equals false sets the change flag to its default no change yet state. About if ignore until is greater than millis. If the current time millis is still less than the ignore until timestamp, a function skips the logic below. This means that while the button is physically vibrating bouncing, the microcontroller ignores the pin, effectively filtering out the noise about else if digital read pin different from state. Once the silent has passed, the function checks if the actual physical value on the pin digital read differs from the last stable state. If they are the same, do nothing. If they are different, that means a valid press or release event has just been detected. When a change is detected, 3 things happen. Ignore until equals millis plus delay. It sets a new LARCAP timestamp for the future, the next 100 milliseconds. During this time, any subsequent mechanical vibrations will be ignored. State equals not state. It toggles the current state from high to low or vice versa to record the new stable condition. Underscore has changed equals true. It flags that a change has occurred. Note: the condition statement, maybe ignore until greater than millis, will work incorrectly, because maybe millis will come back to 0 in the future. We also implement hasChanged. This method returns true only once per state change. After it's called, it resets the internal flag to false. Constant boolean pressed equals mode is equals to input pull-up question mark low colon high. This line makes our code flexible. If you use input pull-up, the button is wired to ground, so when pressed, the pin receives a low signal. If you use input with an external pull-down resistor, when pressed, the pin receives a high signal. The constant pressed automatically adapts to your hardware configuration. In the next lecture, 05.08, we will combine our LED and button objects to create a responsive system. See you there.